right. So you were talking about the electrical dipole, and let me restate that discussion. We talked about the electrical field and superposition and whatnot and all of that. Let me see, whiteboard. Get a new slate. Okay. So, and we wanted to derive the electrical field that comes out of the dipole. Essentially find an expression for it. And the idea is that we want to find, we don't want to deal with the complete expression because it's a little bit too complicated and not useful for us. So we want to derive an approximate formula for the dipole. So what is the dipole? The dipole is essentially, of course, monopole. Give you some terminology. When people say monopole, that's like a single point that has a charge, positive charge, let's say Q plus, Q negative. Some charge by itself, some point charge by itself. This is an electrical monopole. In nature, electrical monopoles exist. The electron is an electrical monopole. The proton is an electrical monopole. When we talk about a magnetic monopole, we mean a particle with a magnetic charge, QM. Those do not exist in nature. We don't find something in nature that has a north pole, particle that has a north pole polarity. What happens is that we find magnets that come up as dipoles. They always come up as north-south pairs. Okay. So although electrical phenomena in nature is rife with monopoles, there are no electrical dipoles. There is no fundamental particle that's a dipole. What happens is you might have an atom. An atom is going to have a nucleus with protons, positively charged protons, and electrons swirling around the atom. So this kind of, like, say, a water molecule, let's say. Well, a molecule is going to have 3 atoms in it, but assume this is something, something like a molecule like this, like an atom. An atom is a dipole. It's called a constructed dipole because portions of it has negative charge and portions of it has positive charge. So the concept of an electrical dipole is natural. It does occur, but it's constructed. There is no fundamental particle that's a dipole, right? What you have is positive and negative charges close to each other that form a dipole. Magnetism, however, monopoles in nature of magnetic polarities do not exist, or magnetic charge. There is no positive magnetic charge and negative magnetic charge. They always come paired with each other. So although we're studying dipoles for electrostatics, the dipole is also an important concept in magnetostatics. And the idea with the dipole is, what is the field of the dipole? So if I have a dipole like this, I can represent the dipole always by its directionality. The dipole has 2 charges in space, right? Q plus and Q minus. So there is always an arrow between them. And that arrow between them, I can represent it as a vector. And that vector represents the direction of the dipole. Now the question is, if I have a certain dipole with a certain D, what would the field from the dipole be at point P? And the idea is that this point P is far, really far away from the dipole, so that it doesn't matter. If I can assume the center of the dipole is here, whether I shift the center towards one of the sides of the dipole, Q plus or Q negative, it won't change a thing. R would not change much. And this is due to the faraway approximation. The idea here, how do you make R large compared to D? The idea is R is much larger than D. You can either make D approach 0, that's one way, or you can make R approach infinity. So typically when we say R is larger than D, what we mean typically is D approaches 0, essentially. The dipole is really close. There's 2 parts of the dipole are really close to each other, to the extent, like an atom. An atom is really tiny, to the extent that you cannot really separate them. So we started the approximation last time with this construction. So this is the center of the dipole. I have my D displacement vector between the Q negative and the Q positive. And then I said I can divide this into half. So this is the center of the dipole. And then I have here d over 2, and I have here another vector d over 2. And then this is my point P. Although I'm drawing everything on a plane, this is 3D. Yes, go ahead.
I do not believe you're sharing your screen.
Oops. Okay, I hope you guys have really good imagination. But this is like a repeat of what we did towards the end of last class. Yeah, so I was talking about the electrical dipole. So hopefully you really had good imagination, and I hope I'm really good at describing stuff. All right, better pay attention always to the shunt window. All right, so this is R. R capital, and then I have, what are the actual distances from the sides of the dipole? So this is a vector here, and this is a vector here, right? So this vector is clearly here we see going this way. We see that d over 2 plus this thing that we were trying to find. We're going to try to find what this vector is, should equal R. So this thing here equals R minus d over 2, right? So this vector here is R minus d over 2. Secondly, we can go, we know that going this way, this vector plus this vector equals R. So we know that minus d over 2, I'm going in the opposite direction of d over 2, plus the vector that I'm trying to find equals R. So the vector I'm trying to find is R plus d over 2. So this is going to be R plus d over 2. Okay, and that those two distances now allow us to construct the field. So I have EP. It's a vector, I guess. I didn't write the vectors notation. It's a vector. So E positive vector, E pole, I guess. Oh, E at point P, sorry, E at point P. Let me say this is negative from the negative charge. This is going to be minus Q over 4 pi epsilon naught R plus D over 2 over magnitude R plus D over 2 cubed. And then EP positive vector is going to be Q over 4 pi epsilon naught R minus D over 2 over R minus D over 2 magnitude cubed. And then we can sum those up together to get the dipole field. So the dipole field is going to be, I can take Q over 4 pi epsilon naught out, it's common. And then I end up with, R plus D over 2 minus, actually, let me do it separately, over R plus D over 2 cubed minus R plus D over 2 over R plus D over 2 cubed. So one approximation we could make is that R plus D over 2 is approximately R, but we don't want to do that. We want to do a Taylor series, what's akin to a Taylor series expansion, right? We don't want to just assume D over 2 is 0, right? So we can take 1 over R plus D over 2 squared cubed. What does this equal? This equals, I want to express this in terms of the dot product. So if I write this as R plus D over 2 dot R plus D over 2. what does this give me? This gives me those two terms here give me R plus D over 2 magnitude squared, right? This is dot product of a vector, but with itself is the magnitude squared of that vector. But I want to get 1 over 3 root square root of 3. So this needs to be multiplied by 1/2, power to 1/2 to get the square root of this, and then powered with -3. So it's going to be -3 over 2. So the right-hand side now and the left-hand side are equal. So this gives me, what's inside the parentheses gives me magnitude squared, and then I square root it, and then I exponentiate it to -3 so that I can take it to the denominator. The reason I want to do this way is now I want to expand this. I want to expand this and hopefully cancel the higher order terms. So if I expand this, I get R dot R, which is R squared. Remember, when I have something without the vector on top, that means I'm talking about the magnitude. This is shorthand for magnitude. So it's going to be R squared, and then plus R dot. So I have then R dot R, and then R dot D over 2, and then another R dot D over 2. So I'm going to have half R dot D plus half R dot D. So I'm going to end up with R dot D. And this is an important term because this now shows relates D, the displacements of the dipole, the directionality of the dipole with the direction of the point in space. So the relationship between them should affect what the field looks like. The orientation of the dipole, although the dipole, we're so far away from the dipole that the two charges are close to each other, the orientation of the dipole is still important. It still affects the field even far away. So R dot D is important. And then I have D over 2 dot D over 2. It's going to become a quarter D squared magnitude. So again, I remove the arrow to represent magnitude. So it's going to be D to the power D squared over 4. Okay. -3 over 2. And then what about the other term? 1 over R minus D over 2 cubed. This equals, I can write this as R minus D over 2 dot R minus T over 2. Again, same thing, -3 over 2. This becomes R squared minus R dot D. Again, I want to keep this term plus D squared over 4 -3 over 2. Now, because the magnitude of the vector D is much less than magnitude of the vector R, I can do, what do you call it? I can cancel this actually. I can cancel this. Okay. I want to cancel this now, and I want to take R squared out. What happens when I take R squared out? R squared out, square root comes R and then -3. So I end up with 1 over R plus D over 2 magnitude cubed. I took R squared out from those expressions, and then I square rooted, I get R, and then I exponentiate it to -3. So it becomes approximately R -3. And then whatever is left inside is going to be, sorry, excuse me, it's going to be 1 plus R dot D over R squared, because I took R squared out. Okay, and then the D squared over 4 I ignore. And then 1 over R minus D over 2 cubed approximately equals R -3, 1 minus R dot D over R squared -3 over 2. Okay, so this was approximation number 1. D is much less than R. The next approximation is we want to approximate this. So we want to use what's called the binomial approximation. Binomial approximation. Let me remind you what the binomial approximation is. The binomial, if you have something like 1 plus x to the power n, where x is a really small number, this approximately equals 1 plus nx. is essentially the expansion of 1 plus x to the power n, where you remove the higher order terms. So there should be plus 1 over n over 2 x squared, blah, 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 stuff like that. And then there should be like higher order terms with x squared, x cubed. I forgot what the exact terms are. But it follows the binomial theorem. But the first two terms are as follows. So what we can do now is we want to get rid of this power. So to get rid of this power, we use the binomial approximation, right? So we end up with 1 over r plus d over 2 cubed, approximately, after applying the binomial approximation. This is going to be 1 plus, and then the exponent here is minus, n is minus 3 over 2. So it's going to be 1. Of course, there's going to be r minus cubed here, right? We are doing the binomial approximation to this. So it's going to be 1 minus 3 over 2 r dot d over r squared. So it's much simpler. We got rid of the power, and then 1 over r minus d over 2 cubed approximately is r minus 3. 1 minus. So this goes down here. This becomes plus 1 plus 3 over 2 r dot d over r squared. So what is ED? Let's see. So we have to take, we just now multiply what we've gotten. So let me see. So we have an approximation for this. We have an approximation for this, and we have an approximation for this. Let me let me just copy it here. Copy. Paste. Okay. So Q over 4 pi epsilon naught is the same. But now both of those terms have r to the minus 3 in them. So there's going to be an r cubed here. It's going to be an r cubed here. And then, why do I have? I think I made a mistake somewhere here. Oh, yeah. That's the computer. There's a minus sign here, of course. I made a typo. No one corrected me. Okay, so there's a minus sign here, and there's a minus sign here. So I can now apply this approximation, right? I applied this approximation. I have r cubed. Both of those have r to the minus 3. I can take it out. I have r cubed here. Now this is going to give me 1 plus 3 over 2, right? So this is going to turn into, let me write it down. This is going to turn into r minus d over 2 times 1 plus 3 over 2 r dot d over r squared, minus the second term is going to be r plus d over 2. And then I'm going to use this approximation. It's going to be 1 minus 3 over 2 r dot d over r squared. Okay. And then I just have to kind of multiply things together. If I multiply those things together, I end up with what? See, I have here r, and then I have here minus r, so that cancels. I have here minus d over 2, minus d over 2, so there's a minus d over 2, minus d over 2. It's going to be minus d. So there has to be a minus d here somewhere. So I have q Oh, okay. I have Q. Come on. Oh, Q over 4 pi epsilon naught R cubed. I have a minus D, right? From D over 2 minus D over 2. And then I have, let me see, I have 3 over 2. I have minus D over 2 times this. And then I have minus D over 2 times this. Also minus becomes plus, so they cancel each other. So you see that minus D over 2 times this. And then minus D over 2 times minus the same term. It's going to be plus D over 2, the same term, so it's going to cancel. A lot of terms are going to cancel. What we're going to end up with is 3 R dot D over R squared R. Only those terms that multiply R will remain. Okay. So this is the expression that remains. It expresses the dipole field at a point R with respect to the distance. And notice, the interesting thing, the magnitude of the dipole field is now proportional to 1 over R cubed. So this is one big difference from a monopole. In a monopole, the field dies away with respect to the inverse square law. With the dipole, plus minus, if you move far away, the field dies down much faster. The field dies down with respect to the inverse cube law. So let's say if you double for the inverse square law, if you double the distance, the field is 1/4 as strong. With an inverse cube law, if you double the distance, the field is 2 times 2, 4, 4 times 2, 8. Is 1/8 of the original strength. Okay, so that field is dying down much faster because it's a dipole. And we want to bring a definition. We want to define something. We want to express, we want to simplify this a little bit further. We want to define something called the electrical dipole moment. Because we don't care about D. We don't know what D is. We don't want to worry about what D is. We want to define something that is akin to charge. So this is akin to charge. This is something like charge. That's what our intention with it is. It is something like charge, only has a direction. So up to this point, we're dealing with sources as being scalar and fields as being the vectors. Here we're introducing a situation where, hey, not every time you have a vector that's a field. Sometimes you can have a vector distributed over space that's a source of another field. So you could have a field that is a source for a field, right? So yeah, when you think electrical, when someone tells you electrical dipole moment, think something like the electrical charge, but has directionality to it. Is a vector quantity, is not a scalar quantity. And where does that vector element comes from? It comes from the orientation of the dipole. The orientation of the dipole in space, the arrow from the negative charge to the positive charge, is what gives the directionality to that source of the electrical field. So we define the electrical dipole moment as a vector source that is just the D, the directional vector, times Q. And the reason we want to do that is we don't want to base our equation on D. We want to base it on something that we define as a vector source of the electrical field. We call it P. What are the units of P? The Coulomb meter. Right? Q is Q, and displacement D is is distance. That's it. So so what I can do is I can take Q inside. If I take Q inside, Q multiplies D gives me P, Q multiplies D gives me P. So the electrical field of a dipole is approximately, of course, 1/4 pi epsilon naught R cubed inverse cube law, and then 3R, the P multiplies the D, sorry, the Q multiplies the D and gives me P dot P over R squared R minus P, Newton per column. So, okay. The dipole moment is proportional to the value of the charge. If you have a bigger positive and negative charge, the positive and negative charges are always equal. If you have a bigger charge, you have a bigger dipole moment. If you have a bigger distance, you have a bigger dipole moment. So it's proportional to both. It kind of encapsulates both. So P encapsulates both the value of the charges of the dipole and the distance. It's like lump them together in one parameter, because ultimately it's the dipole is so small that we really don't care about. I mean, the distance is nothing to us. We don't care about the details of what is coming from the distance between the dipoles or what is coming from the actual charges. Because it's so small, we just lump everything together in one useful parameter called the dipole moment that encodes both the directionality of the dipole and the magnitude of both the charges and the distance between them, right? So it's a useful lumping parameter, and it will become useful much later when we use it. Actually, it has theoretical use in the theory. So the field intuitively is going to look something like this. So let's say I have a dipole. So now I'm going to always write the dipole as an arrow, P, at a point. P meaning, so, okay. When you're in space and I say at the point, this is P. This does not mean that there are two charges, one at, this is the dipole P, and this is point, let's call it point N in space. Point N in space. This does not mean that there's a positive charge here and a negative charge here at the end of the arrow. Remember, P does not encode information about distance. P lumps both distance and charge. All this means is that there's a dipole that's so small, the distance between the charges is so small that we can consider it a point, right? But it has directionality because it's a dipole, and the direction of P points to the directionality of the dipole, and the magnitude of P lumps both the charge and the distance between the dipoles, which is still infinitesimal, okay? So really ideal dipoles, because P is proportional to both the charge magnitude P equals magnitude Q, magnitude D. Really an ideal dipole at a point is something where D approaches 0 and Q approaches infinity. So D would approach 0 and Q would approach infinity. But the product of both of them, one approaching 0 and the other approaching infinity, is a limit, is a certain value, and that certain value is the magnitude of the electrical dipole moment. So think of the electrical dipole moment as this sort of limit, where you want to take a dipole and consider it to be a point source, but it still has directionality to it. So you imagine that the distance approaches 0, the charges approaches infinity, such that the product of both still reaches a finite limit. And that finite limit is the electrical dipole moment. Okay. So what does the field look like? Well, a dipole, we can, I mean, just imagine it something like this. It's going to be, field is coming out, going from positive to negative, positive to negative, positive to negative. It's like a butterfly, positive to negative. And then some field lines fringe out. It's like exactly like a butterfly looking thing. And kind of like the field of a magnet. Remember, because the magnet also is a dipole. Magnets are dipoles in nature. But mathematically, we want to express that. So let's express that as, let's orient the dipole along the z-axis. So I have z-axis. And then I have my tiny dipole here, such that P is oriented along the z-axis. So I have a small dipole here with Q plus and Q negative. Right? It's like at the origin essentially. It's so small, it exists at the origin, but the P is pointing upwards. So we can use spherical coordinates, say. So in spherical coordinates, we know that in this case, z hat equals r hat cosine theta minus sine theta, theta hat. So we know this transformation. Okay, P is just some magnitude z hat. It's pointing towards the z-axis. So the dipole moment is the magnitude of the dipole moment, and its direction is z hat. This is the, yeah. I want to go to spherical coordinates because the field of the dipole is symmetrical. Because it's symmetrical, it's going to be better to go towards spherical coordinates. So we can write, I can write the P in this case as P magnitude r hat cosine theta minus theta hat sine theta. This is just what do you call it? Basis vector transformation, right? But the equation now has what? It has r dot P. So I need to calculate r dot P. What's r dot P? R dot P is the magnitude of r, the magnitude of the distance, the magnitude of the dipole moment times cosine theta. This theta now is the same theta as the spherical coordinate system. Why? Because the dipole is pointing towards the z-axis. So the theta really here is the same, the theta between the dipole and the point in space we were finding the field. So this is direction is r, is really the same as the theta of the spherical coordinate system, because the dipole is pointing towards the z-axis. So this would be r dot P is going to be r magnitude B magnitude cosine theta. That's what the dot product is geometrically. Okay, so now we can write ED as 1 over 4 pi. I'm gonna not write approximate. I'm gonna just assume it's exact, right? Epsilon naught r cubed. So in spherical coordinates, we said we have what? We have 3 r dot P. R dot P is going to be 3 r P cosine theta over r squared. And then r magnitude. R magnitude is what? Sorry, r vector is just the magnitude of r times r hat. That's what r vector is, right? Minus the other term is going to be P. P in spherical coordinates, we wrote it up there. It's going to be P r hat cosine theta minus theta hat sine theta. Okay. So this cancels, this 2 r's cancels this r squared. And so you have 3p cosine theta r hat minus p cosine theta r hat. So I have 2p cosine, I can take the p out, by the way. So this is going to be p. So ED equals p over 4 pi epsilon naught r cubed. So I had 3 cosine theta r hat minus cosine theta r hat. It's going to be 2 cosine theta r hat. And then I have minus is going to be plus sine theta. Okay. Units. What is P? P is Q times D, right? So it says Coulomb meter. And this meter cancels out with the extra R here. So I have an extra R here, which I have an extra meter. So I need P to cancel out with this extra R. So the meter from this extra R cancels this meter, and I end up with Coulomb here. Coulomb over 4 pi epsilon Q squared, sorry, R squared, which gives me the units of the electrical field. And again, we see this field is symmetrical with respect to this field does not depend on phi. So ED is not a function of phi. So as we go, this is the dipole. As we rotate around the dipole, the phi coordinate changes, but that has no effect on the field. The field is symmetrical. So if you have the dipole and then you're rotating around the dipole, you get the same field. The only thing that changes in the field is the azimuth, the theta coordinate. The theta coordinate and the distance away from the dipole. The farther you're away from the dipole, the smaller the field. And then at a certain distance from the dipole, depending on let's say you're this distance, you maintain this distance and you rotate the azimuth. So you could rotate two ways. You can either rotate, so this is the dipole. You can either rotate around the axis of the dipole. In this case, the field does not change. You have the dipole, you're a certain distance. Let's say you're here. You could rotate something like this. Right? In this case, the field does change. Let's say theta is 0. So you're on top of the dipole. So the dipole is here and you're on top. If theta is 0, cosine theta is 1, sine theta is 0. So it's going to be 2p over whatever. So it's going to still change. Right. So you're on the dipole and then you're on top of the dipole. Your field, direction of the field will be in the direction of r hat. So your field will always be in this direction. And it's gonna get smaller based on the inverse cube law. What if theta is 90 degrees? You're here. If theta is 90 degrees, cosine pi over 2 is what? 0. Right? Sine pi over 2 is 1. So now you're in the theta hat direction. So your field is in this direction. ED is in this direction. ED was here. Which makes sense. You know, remember we drew our field lines to go up here and come back like this. So it makes sense that ED is now pointing downwards. But still, the field is still gonna as you go farther and farther, the field is still gonna dwindle in a inverse cube law. What happens if theta equals pi over 2? Sorry, pi. So you start from top pole and you go all the way to pi. Cosine pi is -1. So now the field is pointing in the opposite direction. Right? The field is coming out and then it's coming back in. So that is clearly happening in this in this equation. If you fix theta, let's say fix theta to this theta and move along this line, the field is gonna always maintain the same direction. So let's say this is direction. The field is always going to maintain the same direction because theta is fixed. Notice here theta is fixed. So the field along this ray coming out is going to maintain the same direction, but its magnitude is going to decrease in an inverse cube manner. Let's see if there's an example. So let's see, we talked about, yeah, I want to do an example. Let me see. Calculate the electric field intensity of a configuration as in figure. So this is kind of like what's called an imbalanced dipole. So you could have a dipole where the positive charge is not equal to the negative charge. Which is, by the way, there's a trick to it. There's a trick to it. You don't need to Like let's say someone is kind of like tells you, hey, solve this problem. So you already know how to deal with a dipole, but tells you, hey, what if we have 2q plus and then 1q minus? So the positive charge is double. Right? What you should say? You should say, aha, but you're trying to trick me because now I can use superposition. Right? I don't really need to rederive everything. What I can do is I can divide this problem to two problems. So this is going to be a field due to q minus q plus the field due to q plus by itself. So this is the field really, if you make the dipole unbalanced, what you're really getting is the field, your total field is going to be the field of a dipole, which you can get using this equation. Yeah, this equation, plus the field of a monopole. So that's what your total field is going to look like if your dipole is unbalanced. It will look like, hey, there's some, in this really tiny region of space, there seems to be a dipole, but there is, my field is not exactly a dipole field. There is some extra terms in it. And that extra is the field of a monopole. So what you would do is you would write it as E total equals E dipole plus E Q plus. That's what you would do. And you already have the equation for that. And you know what the equation for this is. It's Coulomb's law. It comes from Coulomb's law. All right. So what's next in this chapter we have to cover? So yeah, I think the final part of the chapter we need to kind of cover is the and we discussed that briefly last time, is how to calculate the electrical fields of charge distributions. Essentially, we know how to calculate the field coming out of a point charge. And we said the idea is that we just apply superposition. We can divide any distribution into infinite amount of number of segments, right? And then the total field is just going to be an integration over the whole thing. So, for example, line distribution. So here we have, and let me zoom this out. So here, for example, you have line distribution, right? So you see here, there's a line segment. So you can imagine there's a wire moving in space here, right? So there's a wire moving in space, and then you divide that wire into really small segments. And this DL hat is one small segment, right? So, so essentially what you're doing, you're finding the field for that small segment, tiny segment, using Coulomb's law, and then you're summing up over the whole line. So, and the convention here, you notice the primes. So there's a convention that people use here, which is whenever you're integrating over space, if you're integrating over a source of the electrical field, you use the prime. If you're integrating over space, over the field itself, you don't use the prime. So essentially what's happening here is that this is part of some big line, some wire. And then you take a tiny segment, DL, right? So this is it, DL prime. And we use prime because this is on the source of the field. We're integrating over the source. And then R is the distance to the point. R is if you have this here, R is essentially the small r in this case. It's a matter of convention. You could use small r or big R. R is the what do you call it, position vector from the origin to the point in space where you're calculating the field. R prime, notice the terminology. R prime is the position vector from the origin to the line segment of the source. And that's why we use the prime notation. The prime, here there's no arrows, by the way, because vectors are just bolded in text, in type. When I use handwriting, I put an arrow instead of, I cannot bold a letter, right? But yeah, I want you to, when you look at this terminology, I want you to understand what the prime means. The prime essentially means is that you have the source of the field and you take a small, tiny segment of it, dl prime, and the prime indicates that you're working on the source. You're integrating over the source. And R prime, the prime here indicates that this is the position vector from the origin to a source of the field. R without a prime indicates the position vector for point in space where you are calculating the field. So as we, this is just, by the way, Coulomb's law, the field as described for a point charge by Coulomb's law. Because here rho L is the line charge density times dl hat. That gives me charge, right? Rho L is Coulomb per meter. dl prime is meter. So Coulomb per meter times meter is just Coulomb. So this whole thing sits in for charge. And then this is just Coulomb's law, R minus R hat. This gives me the distance between the point in space and the source. This is R minus R prime. I don't know why I keep saying R hat. So it represents this vector. Right, so this and 4 pi epsilon. This is just Coulomb's law for a point charge. The idea is that now we apply superposition. So we find the field for this segment, and then we find the field for the adjacent segment, and we sum over the whole line, which could be a bendy line. It's like could be a wire with charge on it, right? And the idea here is that as we're integrating over the line dl prime, what is changing in this integral? Rho L might be changing. It could be a uniform line wire where the charge is equal everywhere, charge density is equal everywhere. It could be a wire where the charge density varies depending on your location. So what we can take in and out of the integral is gonna vary, right? This might be a function of L prime. R prime is definitely going to be a function of R prime because as we're moving across the wire, R prime is going to change because we're going to different points in the wire. R is constant. Why is R constant? Because R points to the point in space where we are calculating the field. And we're calculating the field, in this case, only for a specific point in space. So in this case, R is constant. So it's important in these integrals to know what is changing as you're moving, as you're summing up the integral, and what is constant. What is constant you can take out. What is of the integral, and what is varying you cannot. You have to integrate. Yeah. So I think this is kind of like, I mean, this is pretty. It looks cumbersome, but it's pretty natural stuff. It's all Coulomb's law. So I guess it's good for us to do some examples on that, just to train ourselves. But this is the same thing, Coulomb's law, but now we're integrating over a surface. Notice S prime, notice the notation. Prime indicating that we're integrating, not over space, we're integrating over source material that generates the field. And same thing with the volume charge distributions. So I guess we'll go over I mean, this is just integration, essentially. So just for completeness, we're going to go over a few examples next time and hopefully finish this chapter next time. What did we want to do? Yeah, that's it. Chatty, someone's chatting. Good question. Okay, let's fix the midterm since we're talking about it. How about the 7th? The midterm is going to be take home. It's going to be not going to be through lecture. So how about we do it on the 7th, and then you have to submit it back on the 8th. Is that good? Any veto? Okay, no, that's fair. That's fair. How about the 4th, end of next week? That's good for everyone. No, the midterm, you don't have to even come here. It's gonna be it's a whole day. So I'm gonna submit it in the morning. You have to submit it back by midnight.
Is it like a written and then you take a photo of it? Or...
Written, yeah, scan it and upload it to campus.
Because it's the morning I can't because my flight is at 2 along the phone.
Oh, okay.
Yeah.
All right, sure, we'll work it out. Don't worry. All right, so I'm gonna make a mental note. Midterm is fixed for the 4th, and I'm gonna send an amount. Yeah, single day. It's like a full day exam, so it doesn't necessarily need a date for you to solve it, but I hope it doesn't need a day for you to solve it. But yeah. But I have to remember to send an announcement, or else people will start yelling at me. All right, thank you everyone, and I'll see you next week.